Have you ever wondered why ice melts, but never becomes colder on its own? Why does your phone become warm while charging? And why can't we build a car engine that converts every drop of fuel into motion? At first, these seem like completely unrelated questions. But surprisingly, they all have the same answer. The answer lies in one of the most powerful branches of science, thermodynamics. In this episode, we're going to build the fundamental concepts of thermodynamics, the foundation that everything else in this series will depend on. So, let's get started. When people hear the word thermodynamics, they often imagine pages filled with complicated equations, strange symbols, and impossible calculations. But here's the surprising truth. Thermodynamics isn't really about equations. It's about answering one of the biggest questions in science. How does energy move? Because everything around us depends on energy. Your heart beats because energy is constantly being released inside your cells. Cars move by converting the chemical energy stored in fuel into motion. Even while you're sitting here watching this video, billions of microscopic energy transformations are taking place inside your body every second. So, if energy is involved in almost everything, there must be some fundamental rules that govern how it behaves, and that's exactly what thermodynamics is all about. At its core, thermodynamics is the branch of science that studies energy, how it is transferred, how it transforms between heat and work, and the limits of what energy can and cannot do. Did you notice that last part? Thermodynamics doesn't just tell us what can happen, it also tells us what can never happen. For example, could we build a refrigerator that keeps food cold without using any electricity? Could we design the world's most advanced engine that converts every drop of fuel into useful motion? Thermodynamics gives a clear answer. No, not because engineers haven't tried hard enough, but because the laws of nature simply don't allow it. That's what makes thermodynamics so fascinating. It isn't a human invention, it's the rule book that the universe itself follows. But before we can understand how energy behaves, we first need to answer a much simpler question. Where exactly are we studying that energy? Because scientists don't study the entire universe all at once. Instead, they choose a small part of it to focus on. And that brings us to one of the most important ideas, the system. In thermodynamics, the particular object or group of objects we choose to study is called the system. It could be a cup of coffee, an engine cylinder, a living cell, or even the entire Earth. Here's the key idea. The system isn't something nature defines for us. We define it. We simply draw an imaginary boundary around whatever we want to study and say, "This is my system." But if the system is everything inside that boundary, what do we call everything outside it? That brings us to our next important term. Everything outside your chosen system, the air in the room, the table, the cup rests on, the entire rest of the universe, is called the surroundings. This idea may sound simple, but it is incredibly powerful. Because thermodynamics is really about one thing, the interaction between the system and its surroundings. Heat can move from the surroundings into the system, or from the system into the surroundings. System and surroundings are always a pair. You genuinely cannot define one without the other. It's like trying to describe inside without ever mentioning outside. So, what actually separates these two? What's the line itself made of? That's our next definition, the boundary. The boundary is the real or imaginary surface that separates your system from its surroundings. Think of it as the border between the system and its surroundings. The interesting thing is that the boundary isn't always a physical object. Sometimes it is. For example, if the system is water inside a bottle, then the bottle's walls act as the boundary. But now imagine we're studying a flame from a candle. There's no solid wall around the flame, yet we can still draw an imaginary surface around it and call that the boundary. So a boundary can be real or imaginary. Its purpose is simply to separate what belongs to the system from what belongs to the surroundings. Now here's where things become interesting. A boundary can allow different things to pass through it. Sometimes energy crosses, sometimes matter crosses, sometimes both, and sometimes nothing crosses at all. Depending on what can pass through the boundary, we get three different kinds of thermodynamic systems: open systems, closed systems, and isolated systems. Don't worry about memorizing them because in just a few minutes, you'll recognize them everywhere in your daily life. Let's begin with the easiest one. Imagine boiling water in an open pot. Heat from the stove enters the pot. At the same time, steam escapes into the air. What's happening? Energy is entering the system. Matter is leaving the system. In other words, both energy and matter can cross the boundary. This is called an open system. An open system exchanges both energy and matter with its surroundings. You'll find open systems almost everywhere. A boiling pot without a lid, the human body constantly taking in food and oxygen while releasing heat, carbon dioxide, and water. Even the Earth receives energy from the sun and radiates energy back into space while continuously exchanging matter with its atmosphere. Open systems are incredibly common because very few things in nature are completely isolated. Now suppose we close the lid. Does the system still behave the same way? Not quite. Now the steam can't escape, no water enters, no water leaves. The amount of matter inside remains the same. But the stove is still heating the pot. That means energy is still entering. So what changed? Matter can no longer cross the boundary. Energy still can. This is called a closed system. A closed system exchanges energy with its surroundings, but not matter. Imagine a pressure cooker with its safety valve closed. The food remains inside, but heat from the stove continuously enters the system. So whenever matter stays inside while energy is free to move, you're looking at a closed system. But what if we could stop everything? No matter, no energy, nothing entering, nothing leaving. Would such a system exist? Imagine the perfect thermos, one so well insulated that no heat enters, no heat escapes, nothing is added, nothing is removed. This is called an isolated system. An isolated system exchanges neither matter nor energy with its surroundings. In theory, it's completely cut off from the outside world. Now here's an important point. Perfectly isolated systems are almost impossible to create in real life. Even the best thermos flask slowly gains or loses a little heat. Every container leaks at least a tiny amount of energy over time. So isolated systems are mostly ideal models that help scientists understand thermodynamic principles. The closest practical example is a high-quality vacuum flask, which greatly reduces heat transfer, but never eliminates it completely. For most scientific calculations, however, we often assume a system is isolated if the exchange is so small that it can be ignored. That's one of the beautiful things about science. Sometimes we simplify reality to understand it better. Now we've learned about the system, the surroundings, and the boundary between them. But here's one final question. If we combine the system and its surroundings together, what do we get? The answer is beautifully simple. The universe. In thermodynamics, universe equals system plus surroundings. Every thermodynamic problem, whether it's a chemical reaction in a laboratory, an engine in a car, or a cup of coffee cooling on your desk, can always be viewed this way. Choose your system. Identify its surroundings. Understand what crosses the boundary, and together, they form the thermodynamic universe you're analyzing. This simple framework is the foundation of everything we'll learn in this series. We've learned what a system is, but now another question naturally follows. How do we describe a system at any particular moment? Imagine I hand you a sealed bottle filled with gas. Without opening it, how would you describe its current condition? You'd probably ask questions like, what is its temperature? What is the pressure inside? How much gas does it contain? The answers to these questions completely describe the condition of the system at that particular instant. And in thermodynamics, this condition is called the state of the system. Think of it like taking a photograph. A photograph captures exactly how a person looks at one particular moment. Similarly, the state is simply a snapshot of the system at a specific instant. But here's something important. Simply saying a system has a state isn't enough. We need a way to describe that state using measurable quantities. These measurable quantities are called system variables, also known as state variables. They are the properties that tell us everything about the system's current condition. Some of the most common state variables are temperature, pressure, volume, mass, and density. Together, they form the language through which a system tells us what's happening. But not all state variables behave in the same way. In thermodynamics, they are broadly divided into two categories: extensive properties and intensive properties. Let's understand the difference with a simple example. Imagine you have a glass containing 1 liter of water. Now, pour half of it into another identical glass. Let's compare the two glasses. The amount of water in each glass is now different. So, the mass of water in each glass is different. The volume is also different. And if you pour the water back into a single glass, both the mass and the volume simply add together. Properties like these depend on how much substance is present. They increase or decrease as the size of the system changes. These are called extensive properties. Mass, volume, number of moles, and total internal energy are all examples of extensive properties. Now, look at the thermometer. Both glasses still have exactly the same temperature. The pressure also remains unchanged simply because we divided the water. Even the density stays the same. These properties do not depend on the amount of material present. Whether you have 1 liter of water or half a liter, their values remain unchanged. These are called intensive properties. Temperature, pressure, density, concentration, and many other properties belong to this category. This distinction may seem small right now, but it's one of the most important ideas in thermodynamics. Let's quickly bring everything together. Thermodynamics is the science that explains how energy behaves. To study any thermodynamic problem, we first define a system. Everything outside it becomes the surroundings. The boundary separates the two and determines whether energy or matter can cross. Depending on what crosses the boundary, systems are classified as open, closed, or isolated. Every system has a state, which describes its current condition. That state is defined by measurable properties such as temperature, pressure, and volume. And finally, those properties are divided into extensive and intensive depending on whether they depend on the amount of substance. These ideas may seem simple, but they form the vocabulary of thermodynamics. With this vocabulary locked in, we're finally ready to dive back into the laws themselves, starting with the first law and exactly how energy keeps its perfect, unbreakable balance sheet. If this made the definitions finally click for you, then you click the like, subscribe so you don't miss it, and share this video with someone who thinks thermodynamics is just a collection of difficult equations. I'll see you in the next episode, but before that, tell me in the comments, which term do you think you'll use the most going forward?